Alright, so let's take a look at our first example of solving a system of equations by graphing. So here's our first one. I need to solve the system with these two equations. Y equals negative x plus 2 and y equals 2/3 x minus 3. Now I'm going to color code these in blue and red so you can tell which graph goes with which equation. Okay? Alright, so let's tackle this one in blue first. Now hopefully you've noticed that this equation is in slope-intercept form. Y is by itself, which means that I can just pull the graphing numbers straight from the equation. So the y-intercept for the one in blue is 2, positive 2. So on the y-axis I'm going to go to 2. And then my slope, it's not there right now, but we know that there's an invisible 1 right here. And then to make that a fraction, we'll place that over another 1. So my slope is negative 1 over positive 1. So from my starting point, I can go down negative 1 over positive 1, repeat it a few times, and then get a ruler. And especially with this type of stuff, accuracy is super important. So you want to be as close as you can to exact, because remember, it's the solution is where these two lines intersect each other. And if you're even a little bit off, you're not going to get the right solution point. All right, so there's the one in blue. Now let's take a look at the other one, which also happens to be in slope-intercept form, which means my y-intercept is negative 3. And my slope is 2/3. Rise 2, run 3. So rise 2, run 3. Rise 2, run 3. And again, if I carefully graph it, I have my system. Now, once again, what we're looking for is we're looking for the one pair of xy coordinates that works for both equations. Or in other words, the one point that these graphs both share, which is right here. The only xy coordinate pair that is the same for both lines is right there, which are the coordinates 3, negative 1. So that tells me that not only do these graphs share that location, that these equations share this x and this y as answers. And in fact, what I'm going to do is I'm going to check my work over here. So let's take a look. I'm going to check the one in blue. All right, so on the one in blue, it's y equals negative x, oops, start over there. Y equals negative x plus 2. And for x and y, I'm just putting parentheses. And then I'm going to take this coordinate and put it in. So x is 3, y is negative 1. And if I do the math there, negative 1, and then negative 3 plus 2 is also negative 1. That point works as a solution for that equation. Okay, but I also need to check it for the one in red. So let's try that. Y equals 2/3 x minus 3. And again, for x and y, I'm going to plug in my solution point. X is 3, y is negative 1. Check the math. Negative 1 equals 2/3 of 3 is 2. And then 2 minus 3 is negative 1. Okay, so this one also checks out. All right, so it turns out that this intersection point between my two lines is the one shared solution to the two original equations. So my solution to the system is x is 3, y is negative 1. All right, let's take a look at a second example. Here I've got another system we're going to solve by graphing. But notice, unlike our first example, these are not in slope-intercept form. In fact, hopefully you recognize that these are in standard form. So because they're in a different format, we're going to solve them in a different way. So let's do the one in blue. For standard form, it's easier if we find our x and y intercepts by plugging in zeros. So for the x-intercept, plug a 0 in for y, which means 3y will disappear. And I get negative x equals negative 6, which if I divide both sides by negative 1 means x equals 6. So we have an x-intercept of 6, 0. All right, then I do the y-intercept by plugging in a 0 for x. So if I plug the 0 here now, this disappears, and I get 3y equals negative 6. Divide both sides by 3, y equals negative 2. So we have a y-intercept of -2. And if I connect those, I'll get a graph that goes here. And once again, I want to be as accurate as possible so that my two lines will intersect in the right location. All right, so like that. All right, let's do the one in red now. I'll put this work down below it. Same thing, it's in standard form. So our most convenient method is to plug in zeros. So if I plug a 0 in for y, 3y disappears. I get -5x equals 6. Divide both sides by -5. So x would be -1 and 1/5. So that's my x-intercept. Now, always with the fractions, just come as close as you can, but really be as accurate as possible. So -1 and 1/5 would be right there. All right, let's try the y-intercept. Plug a 0 in for x. -5x will disappear because of the 0. We get 3y equals 6. So when I divide both sides by 3, I get y equals 2. All right, so we get a y-intercept of 0, 2, which goes right there. So when I graph that one, it's going to look like this. So it looks like my intersection point is right here, which is the coordinates -3, -3. And so once again, the logic is this. If these two lines share this point and only this point, then the original equation should share the solution x is -3, y is -3 as an answer. All right, so let's check our work. I'll put the check for the blue one right here. So again, to check it, we take our equation, -x plus 3y equals -6. And I'm just going to leave a blank for x and y. And we're going to take our answers and plug them in. So x is -3, y is -3. Negative and then -3 in the parentheses. The two negatives will cancel out. It'll be 3 plus 3 times -3, which is -9. And 3 plus -9 is -6, which checks out. All right, so that x-y pair works for the equation in blue. If we've done it right, it should also work for the equation in red. So I'll put that one right underneath there. So the original equation, -5 times x plus 3 times y equals 6. And if I move it up, you can see it. So -5x plus 3y equals 6. And again, take the same pair of coordinates to see if those work. -3, -3. -5 times -3 is +15. 3 times -3 is -9. 15 plus -9 is 6, which equals 6, so that also checks out. So our answer is correct. So this point that both these lines share are also the solutions that these two equations share. So we've solved the system.